In Chapter 11, we turn our attention to liquids. This is the middle chapter of a three-chapter sequence that's about the properties of gases, liquids, and solids. We're going to take a close look at the forces that hold the molecules together in a liquid, and then later we'll look at some of the properties of liquids. But we start by comparing the properties and the characteristics of gases, liquids, and solids. This table sort of summarizes the macroscopic differences between these three states of matter. And a lot of this is going to be intuitively familiar to you, right? We know that if you put a gas into a container, the gas will expand to fill the container and take, the shape and the volume of the container. Whereas a solid, it has its own particular shape and volume, and its container doesn't matter. A liquid is a little bit in between. Like a solid, the amount of space or the volume occupied by the liquid is really independent of its container. But it can take the shape of the container that it's in. We'll also see that gases are easily compressible. Just imagine if you had a balloon in your hands, it wouldn't be too hard to squeeze that balloon and make the volume smaller. But solids and liquids have very small compressibilities. We could think of them as being virtually incompressible. And of course, the other characteristic that's different has to do with the flow. A gas will flow into the open space. A liquid, if given the right force, of course, can flow. But a solid doesn't really flow. So we see that a liquid, not surprisingly, is a little bit in between the gas and the solid. If you look at the states of matter that are represented by the elements on the periodic table, as we see here, we'll see that most of the elements are solids at ambient conditions. There's a little corner up here in the upper right that's occupied by gases, and we see that liquids are in fact incredibly rare. Of the commonly found elements, we only find two that are liquids at room temperature and pressure: bromine and mercury. This one here, Copernicum, element 112, is only made in a particle accelerator, and I doubt that actually enough atoms of this have ever been made to really make a proper liquid. So I bet that's a prediction of theory. We see that group 17, the halogens, are rather interesting because the top two members, fluorine and chlorine, are gases. Bromine is a liquid, and iodine is a solid. So they make a good case study for what is the difference between solids, liquids, and gases. If we look a little bit more carefully at the melting points and the boiling points of the halogens, we get this picture. So bromine melts at 266 Kelvin, actually not very different from water itself, and then it boils at 332 Kelvin. So it's got a liquid range of about 70 degrees. And that you can see that it's a solid for quite a wide temperature range. Then it's a liquid for a fairly narrow temperature range. And then it becomes a gas. Okay, and if we look at the other halogens, we can see similar trends. From this graph, I would take away 2 points. Firstly, that as we raise the temperature, substances will transition from being a solid at low temperature to a liquid at intermediate temperature to a gas at high temperature. Another takeaway point is the fact that the liquid range is generally fairly narrow. Most substances are not liquids for wide temperature ranges. There is, however, another question presented by the data here, and that is, why does the temperature range over which we see a liquid shift to higher temperatures as we move down the group? And that's something we're going to get at in the next section. Here's another look at chlorine, bromine, and iodine. What you see here is, chlorine is this green gas. It's toxic. You don't want to be breathing this stuff in. Bromine is this maroon-colored liquid. It has a pretty high vapor pressure at room temperature, so you can see that there's a lot of bromine even in the gas phase here. But there's definitely a liquid. And then iodine is a crystalline solid that's got a kind of a dark violet color. If we looked at the molecules inside each substance, we would see that the chlorine molecules are very far apart from each other and moving rapidly. And that rapid random motion is why a gas will expand to fill its container. But the liquid and the solid look, pretty similar to a first approximation. The molecules are packed together rather tightly, and that's what makes them really difficult to compress. The difference, which doesn't come through so much in this image, has to do with the freedom of motion of the molecules in a liquid versus a solid. And to get a better sense of that, we're going to turn to a PhET simulation from the University of Colorado that shows a molecular level picture of liquids, solids, and gases. Here's our simulation. In this simulation, we are going to be able to switch between different substances. We could look at noble gases like neon or argon. We could look at oxygen, which is a diatomic gas, or we could look at water. But we're going to stick primarily with oxygen because it's a diatomic molecule just like the halogens. Now, if you look closely, you'll see that there are pairs of oxygen atoms that are stuck together, right? And that represents the O2 molecule. And so the bond that holds the two oxygen atoms together in the molecule, that's a very strong covalent bond, and at no temperature that we can access here is that bond going to come apart. We're starting off at a really low temperature, 27 Kelvin, because of course oxygen is a gas at room temperature and you have to get it pretty cold to get into the solid state. In fact, oxygen freezes at 54 Kelvin. Now you can see that there are vibrations of the molecules. They're not just sitting still, but they're not moving around, right? They're not trading partners. They're not moving from one side of the sample to the other. And so the kinetic energy that's present in a solid is largely expressed as vibrations of the molecules. If we were to cool this down, let's go as cold as we can, maybe down to 1 or 2 Kelvin, what you see now is at 2 Kelvin, there's hardly any motion of the molecules. Just a tiny, tiny bit. And in fact, that's what we mean by absolute zero on the Kelvin temperature scale. That's where all the thermal motion would cease. Let's warm this thing up to the point where it's a liquid. Okay, so we're now at a temperature of 57 Kelvin. Right, that's a few degrees above the melting point of oxygen. And the one thing we see as the molecules are still quite closely packed, not really that much further apart from one another than they were in the solid state. But they're moving around a little bit, okay? And so they have more freedom of motion. And let's heat this up a bit to maybe, we can go up to maybe 80, 85 Kelvin, and it should still be a liquid at that temperature. And what we see as we approach the boiling point of oxygen, which is 90 Kelvin, is that now there's quite a bit of jostling of the molecules. They are moving around, they're changing partners, but for the most part, they're still staying cohesively stuck together. Occasionally, a molecule will break away and go off into the gas phase. That creates something that's called vapor pressure, and we'll talk about that later in chapter 11. But let's now heat it up more. When we get to, in the 90s here now, we're above the boiling point of oxygen. And now you see the molecules have moved to fill their container. They're getting away from each other, but they're also still a little bit sticking to each other at time to time. And back in chapter 10, we talked about gases, and we said, there's ideal gases, but then there are deviations from ideal gas behavior. And one of those happens at low temperature, because at low temperature, there's a non-negligible force of attraction between molecules, and that reduces the pressure of a real gas. And we can see that's the case here. If we were to heat this up further, let's see if we can bring it up to room temperature or above. As we heat, we're adding more and more kinetic energy to the molecules. And you can see that they're moving around a little bit faster. We also see that the propensity for them to stick together is lessened. As they have more kinetic energy, they tend to bounce off each other more elastically, and we get behavior that's more like an ideal gas.